Okay, so welcome back. As I said in the chat, I'm having a bit of an issue with a tooth, so I'll try to not ramble too much if I'm distracted by the pain. But anyway, so first thing, reminder that you have homework due tonight. So you still got plenty of time. You still got what did I say? I think I said it's due at midnight, so you still got more than 12 hours. Do the cats also have my weird sleep schedule? Yes, they do. Um, they do. They've inherited that from me. Basically, what I wanted to do today is start on the meat of chapter 12, which we kind of built up last time from talking about vector valued functions. So we spoke of vector valued functions. So this was typically the notation for some general vector valued function. Uh, so we have these three component functions. Of course, a completely equivalent way of writing this is using our other notation for a vector. So that those are just the functions of t that make up the components of this vector valued function, big F. And the idea was that every property that we would want big F to have, or every, if I wanted to try to translate the concepts from Calc 1 and 2 over to vector valued functions, the idea was that I could do it component-wise. So anything I wanted to talk about, I could just impose those conditions on the components. So for instance, we could say that big F is continuous if all of the component functions were continuous at a point or on an interval, right? So typically this T is defined, this is for all, T in some domain D, which is a subset of the reals, okay? Um, and so if I wanted to talk about a vector value function being differentiable, then it was differentiable at a point if each of the component functions were also differentiable at that point. Okay, and so we even talked about some things last time. So for instance, assuming that the derivative of each of the component functions existed, then we could even write out this vector valued function that we called the derivative of big F, or f prime of t, which was exactly what you think it should be, right? It is just the vector valued function that contains the derivatives of each of these component functions of big F. All right, so this is important. We're going to be doing this over and over again. I mentioned, last time you could also do the same thing with integration, but that's going to be less useful for us for what we want to do. Okay, and so, of course, there's all kinds of properties of vector valued functions that I could talk about. And so this is the bit that I'm going to skip over. So like 12.2 to 12.3 is almost entirely skipped. When I say skipped, I am going to cover everything that we need from those sections. So there are going to be properties that we use that come from those sections, but I'm not going to spend too much time actually listing every single thing. So the main point is just like I could define pointwise addition or pointwise multiplication for real valued functions. For vector valued functions, I can do similar things. So if I have two vector valued functions, say big F of t and big G of t, right? Using the same notation, so this has component functions, little g sub 1, g sub 2, and g sub 3. Then I can form things like here I'm going to write it like this. So I can form things like big F plus or minus big G, right? And what would that vector valued function be? You know exactly what it is. It's just going to be the vector valued function that you obtain from adding each of the components, right, in each slot, or subtracting, since I've done plus or minus here. Okay. And similarly for other types of algebraic operations you might want to do, like scalar multiplying, right? Works the same way. Okay. So I could talk about, C times big F of t, and it's just me scaling every component function by the scalar c. Okay. So then when it comes to multiplying, of course, well, here's the key thing to remember, right? With vector valued functions, you can make your life easy, and we are doing this over and over again. That's why we're able to say all these things. That at a particular t, right? So at a fixed t, f of t is a vector, right? That's the definition. Okay. And so at some given t, both f of t and g of t are two vectors. So multiplying them has the exact same properties of just multiplying two vectors. And so we can do this pointwise, right? So we could define what it means to cross two vector valued functions, right? What does that mean? That means exactly what you think it means, right? It's that I literally form the cross product of, where what goes here is a function of t, right? Okay, so this is what I can do. I can also dot these two things. All right, so I can dot two vector valued functions. And of course, what I get is exactly what you expect. F sub 1 of t, g sub 1 of t, plus f sub 2 of t, g sub 2 of t, plus f sub 3 of t, g sub 3 of t. Okay, and now, what do we note? Well, the cross product of two vector valued functions is itself, if we work this out, a vector valued function. Okay, but the dot product of two vector valued functions is a function of t, but it is scalar valued, right? And so here is a good example of why we have introduced another word for constant, right? We know that a scalar is a constant. It's just a real number, right? But why might we want to use scalar over constant sometimes? Because it can be confusing if I were to call this constant valued, right? Because we know what it means. If we say that a function of t is a constant, well, that means that it takes on a single constant value, right? So if we called something constant valued, but we meant scalar valued in this way, it would seem a little weird because that you might get confused and think that you're saying that it's a constant, right? But it's not a constant. It is scalar valued or real valued, right? So this is just a real valued function on the right here, okay? So the cross product of two vector valued functions is a vector valued function. The dot product of two vector valued functions is a real valued function or scalar valued function. Okay. All right. I'm not going to really do anything with this. There is one application we have for this. Okay, and I will come back to it when we need it. Your textbook does this in 12.3, but I'm going to wait and do it when we're talking about what we need it for. Okay. Now, all this algebra is nice. So there's various nice algebraic properties that I won't get into. If you're interested in those, you can look at 12.2 or 12.3. What is the purpose of talking about vector valued functions? So the main purpose of VVFs in this class are to describe curves in the plane and in space. Okay, so this is the main purpose of vector valued functions. All right, well, what does this mean? Right. You've already seen an example of a vector valued function used to describe a curve, okay, in the plane. In fact, if you took Calc 2 at UMD, then this is the last thing you do in the class. Okay, so let's say that I want to consider the following vector valued function. So consider the vector valued function cosine of t I plus sine of t j. And t lives in the interval 0 to 2 pi. Okay. What is this? let's write this another way, right? If we write this another way, this is cosine t in the first slot and sine t in the second slot. What is that? You've definitely seen this before. So I'll wait till someone says something in chat. Yeah, it's unit circle, right? This is unit circle. So if I were to start at t equals 0 here, right? So to see what it is that's going on here, so f of 0 is cosine of 0i plus sine of 0j, right? So this is the vector 1, 0, right? So that's here. Right, so this is when t is equal to 0. Okay. What about when t is equal to like pi over 4, right? So f of pi over 4 is cosine pi over 4 I plus sine pi over 4 j, which is root 2 over 2 I plus root 2 over 2 j. So that's like here. Right, so here's when t is pi over 4. And of course you can plug this in and see that, oh, well, this is what the full picture looks like. That's a really bad circle. Okay, but this is what it looks like, and here is when t is pi. Here is when t is pi over 2. And here's when t is 3 pi over 2. And when t is 2 pi, we're back to the starting point. Okay. And so what are we thinking of? We're thinking of this vector valued function describing a vector at each point that is, so it begins pointing at the point 1, 0, and then it starts pointing at all of these points around a unit circle, right? We know that if I consider, right, what set, all right, what geometric object is defined by the set of all points, cosine ti plus sine tj, as t runs from 0 to 2 pi, well, it's that unit circle, right? It is once around a unit circle, starting at 1, 0, going once around. Okay. So what if, here's another, so this was one example. Here's another example. What if my vector valued function is exactly the same, right? Algebraically, right? The form of it looks exactly the same. But I consider t going from 0 to 4 pi. Right. Is this the same vector valued function as this? Well, no, right? It's not the same. Okay, in fact, it has a different domain, right? So it has more data, right? But what is it that's going on here? If you were to draw this, however, it would look the same just looking at it. But if you actually trace out what's going on here, well, you go once around the circle, that's 0 to 2 pi, and then you go once more around the circle from 2 pi to 4 pi, right? And so if you were thinking about these two things as curves, this curve would be going once around a unit circle, and this curve would be going twice. Okay. So it looks, just looking at it, it looks like the same curve, but it's not. Okay, it's not. And one way that we'll distinguish between them is we can compute the length of those things. But before we do that, we have to nail down that this is exactly the type of thing that we want happening. Okay, and so vector valued functions are going to be used by us to describe curves in the plane and space. So this was your first example when you did this in Calc 2 or whenever you've seen this before. This is your first example of what's called a parametric curve. So this is a parametric curve in the plane. Now, what is the benefit of talking about curves parametrically? The benefit is that before you use parametric curves, or before you describe curves parametrically, if I ask you to do any kind of calculus stuff, okay, if I ask you to do any kind of calculus stuff on a curve, and it looks something like this, then if you're not using a parametric description of it, you basically can't do anything. Why? Because in order to do calculus in the usual Calc 1 sense, you need to be talking about a function. But is this the graph of a function? No, right? It fails the vertical line test, right? A circle is not the graph of a function. Sure, you could split this thing up and talk about the upper semicircle and the lower semicircle separately, right? But then there's some issues. There's some issues with these overlapping points, how you connect those. Okay, so there's a lot of problems there. It's very complicated. But I don't have to worry about that at all if I use a parametric description, right? There's absolutely no issue here. Okay, and so the main strength of describing curves parametrically is we never have to worry about this business of, oh, is it a function, right? Is it the graph of a function? Because clearly this is a very simple example showing that, I mean, it's not the graph of a function, but we can perfectly describe it like this. Okay, and so this is one of the strengths of describing things parametrically. It allows you to do calculus on curves that look like this, right, that are not graphs of functions. Okay, and of course we are able to do that by coming up with this parametric description. Okay, so then what is the idea? So this idea is going to be illuminated by a particular example. Okay, so let's choose another vector valued function. And here's my vector valued function. So minus 1 plus 3ti minus, say, 5 plus 2tj plus tk. Okay. I don't know why I put k inside the parentheses there. Let's rewrite this. It's bothering my... Okay. There we go. And t ranges over all the reals. Okay. So this is a vector valued function. Okay, so this is a VVF. What does this describe though, right? So what object is described by the collection or set of all vectors big F of t as t ranges over all of R? What object is described by this? So if I say consider the set of all vectors big F of t, where t ranges over all the real numbers, what does this describe? It's a line, right? This is the parametric description of the line, right? So this is a line, right? Given parametrically. All right, this is just the statement that x, right? So we have a function that depends on t, x of t, that is minus 1 plus 3t. We have a y of t function that is, well, I'm going to distribute this. So this is minus 5 minus 2t. And a z function that depends on t, that is, 0 plus t. Okay. And so this is just the parametric description of this line. Okay, so a point on the line you can read off is minus 1, minus 5, 0. You can immediately read off a vector parallel to it, 3, minus 2, 1, right? Okay, and so remember in our picture, right, when I drew this parametric description of line, what was the idea? The idea was that I had some r naught vector, which was my initial, this vector pointed to that initial point, P naught. And my line in space, well, that was really bad. So my line in space, of course, looked like this, passing through P naught. So here's my line L. And if I wanted to think about what was going on, I had a generic vector R. So maybe here's what R looks like at this point. So this generic vector R of t is tracing out this line. So here it is initially, right, if you want to think about t equals 0 being like an initial time. And as t varies over the reals, this R of t vector traces out the line. Okay, and I hinted before that that's a good way of thinking about how to parametrically describe a line in space, because if you think of this vector as tracing out this line, well, then it's not that big of a stretch to imagine a vector tracing out not a line in space, but a curve. Okay, and so that's exactly what we want to do from this. Okay, so then what is my idea? My idea is that I have space here, and here's a curve in space. Okay, and I want to think of a vector R of t, okay, that as t varies, right? So as t lives in some domain D, okay. Now, oftentimes, right, D is going to be a closed interval. Or D could be all of R, or some more complicated subset of R, right, that I'm not going to write out more examples of. But frequently, you know, this is what you see. So if you have some infinite curve, D might be, you know, all of R. If you have a curve that actually has endpoints, then D is going to be some closed interval, typically. Okay, and so the idea is that I have some curve in space, and this vector R of t, as t varies over its domain, traces out that curve, right? So maybe here is what R of t looks like at some other t value. So this is, say, some t naught. Here, this is R of t sub 1. Here, it is at R of t sub 2, and so on, right? So this is how the curve is being traced out by this vector. Okay. Well, what do we need in order to have a curve in space traced out by some vector R of t? Well, our notation is going to be the following. R of t can be thought of as a vector-valued function that has three components: x of ti plus y of tj plus z of tk. Okay, and t is in some domain D. Okay. All right. So what is this? Notice this is just a VVF. So this is just a vector-valued function. Okay, we've just changed this, you know, notation slightly. Instead of calling it big F, we call it R, and instead of calling these things f sub 1, f sub 2, and f sub 3, we call them x, y, and z, and they're functions of t. Okay. And so this is the parametric description of a curve C in space in R3. And of course, everything that I'm doing conceptually here, as far as this notation goes, if I drop this entirely and talk about curves parametrized as x of ti plus y of tj, I can do this for curves in the plane. So now here's kind of this is a thing that's kind of a philosophical distinction, but it is important that I mention this because it can be confusing. So how do we typically encounter this, right? You might say in the wild, how do you encounter a curve? Maybe you encounter a curve as just listed as some curve C, right? And then given a curve C, you can come up with this, which is called, so R of t is called a parameterization of the curve C. Okay. And so C, this curve, is the object that we're asking questions about, that we're studying. But in order to help us study this object, we come up with a parameterization, which is a way of describing that curve. Okay. Now, the second that we come up with this, you notice this is a different question now. So we've passed from the curve as geometric object, and now we've come up with a parameterization of the curve, which is a description of that curve. The first question you have, is a parameterization unique? Right? So is there only one parameterization of a given curve, or are there several? So I'll give you a couple of seconds to think about that. Think about what the answer is, just based on what you know coming from the plane, or just thinking about it for a second. So the question is does a curve have a unique parameterization? Or are there multiple ways, possibly, of parameterizing a curve? So, while you all are thinking about that, I'll look back to chat here in a second. I'm going to start on the following example. And again, just as it turns out, and this is true not just in Calc 3, but even when I'm teaching like Math 436, which is literally an entire course devoted to curves and surfaces in the plane and in space. Whenever you want to study something and really understand it, you do it in 2 dimensions. And yes, there's some things that you can't really carry over from 3 dimensions to 2 dimensions. There are some differences, but there's a lot that you can understand by looking at the 2-dimensional case first. Vectors are just a point, so there's probably multiple ways. I don't think so if it's at the same point in space. Okay, so some mixed ideas here. So here's the example that I'll give. So let's consider 2 curves. Okay, let's not consider 2 curves. Let us consider a single curve. Okay, and I'll tell you why I was laughing here in a second. So let's consider a curve that is, let's say, a circle of radius 2 centered at the origin. Okay, so here's the point 2, 0. All right, and so this is going to be a bad circle. Oh, it wasn't as bad as I thought it would be. So here's a circle radius 2 centered at the origin. Here's C. So let C be the circle of radius 2 centered at the origin in the plane. Okay, so circle, radius 2, centered at the origin. I'm going to come up with one parameterization of it, so you all can help me with this. Give me a parameterization of this circle. Okay, so we just did it for unit circle. How would I need to change that in order to alter what's going on here? Right? How would I need to change that to make it work? So if this were unit circle, my parameterization looks like what? Looks like, cosine ti plus sine tj is great for us if this were unit circle. How do I need to change this, since this is not unit circle centered at the origin? This is circular radius 2 centered at the origin. Yeah, in the I and J slots, you just have a 2 out front, right? So this works. Okay, so 2 cosine ti plus 2 sine tj. And of course, when you describe a curve, when you write out a parameterization, I'm going to beat you all over the head with this several times because it's very important. When you write out the parameterization of a curve, you're not done until you say where t lives. Okay, why? Well, if I don't specify, the possible values of t, then what curve is this? Does it go 10 times around the circle? Does it go counterclockwise, clockwise? What's going on here? right? So then I have to say, where does t live? So t lives from 0 to 2 pi. Okay, so that is a perfectly fine parameterization of my circular radius 2 center at the origin. Okay. All right. So now I'm going to give another one. So let's do 2 cosine of 2t I plus 2 sine of 2t j. And t lives from 0 to pi. Oh, someone's asking what symbol comes after t. So this is a I actually don't know the name of this symbol, but this is \n. So when you see t is in D, what does this mean? This means t is in D. So that symbol is read like this. Okay, in LaTeX, this symbol is \n. Okay, so literally means that something is an element of the set that follows. Okay. All right. So what did I do here? So I claim that both of these are perfectly fine parameterizations of C. Okay. Chow Wei, exist is a backwards E. So exist looks like this. So this means there exists. Yeah. Which I will write sometimes, but usually I'll try to use words for that. I don't usually bring the hammer down on. I don't bury you under notation like that until usually Math 310 and up is when I start burying students under that notation. So the most common ones I'll use here is this. I will use this constantly. Okay. Yeah, so as Brandon said, the domain that t is in is smaller, but that doesn't change what curve is being described here, right? It's the exact same curve that's being described. Even the direction is the same, right? So if you actually trace the points, both of these parameterizations are going counterclockwise around the circle. So what's going on here, right? Think about physics for a second. Physically, if you were trying to describe what's going on here, what would you say? So the hint is, this, what's the relationship between these two intervals of t? So one of the things that confuses students the most when they see parametric descriptions of things is that t lives in a window. But where is t in this picture? Well, it's invisible, right? T is a parameter that lives somewhere else. It's not visible. So unlike when you're graphing something that has an x and a y component, right, you can actually see here's the x value, here's the y value. So any point has an x and a y value. But this parameter t lives, off screen, right? It lives somewhere else. That's actually the strength, that's the power of this method, is because we have a parameter that lives not in a dimension that is indicated here, that's describing these points. Okay, that's how we can get around this issue, right, of these things not being functions. Okay, so if I actually started plotting points, right, so here I'm going to do this for R1 first. So for R1, when t is equal to 0, I'm here, right? So here's t equals 0. Okay, when t is equal to pi over 4, where am I for this parameterization? Well, I'm here. Right. Okay, and when t is equal to pi over 2, of course, I'm here. Okay, and when t is equal to pi, I'm here. So just like before, right? Here's t equal to 3 pi over 2, and back here, this is t is equal to 2 pi. Okay. All right, now let's do the same thing for this curve, right? So at this curve, when t is equal to 0, I'm still at the same starting point. But when t is equal to pi over 4, where am I? So let me delete these crudely. Okay. So now I'm doing this for this second parameterization. So when t is equal to 0, I'm still here. But when t is equal to pi over 4, where am I? So I would have 2 cosine of 2 times pi over 4, but that's pi over 2. So that's here, right? So when t is equal to pi over 4, in this parameterization, I'm here already, right? Whereas before, I was at this point. Similarly, when t is equal to pi over 2, I am at, so this would be 2 cosine of 2 pi over 2, so that's pi, right? I'm here, so this is when t is pi over 2. Okay. Similarly, when t is equal to 3 pi over 4, I'm here. And finally, I'm back to my starting point when t is equal to pi. So what can you say about the second parameterization, right? So R2t goes around C twice as fast. Okay. But if all I'm doing is describing the curve C itself, I didn't mention anything about how fast I'm going, right? I don't even have a concept yet of what fastness means going around a curve, right? And so I didn't include this anywhere, right? So because of that, these are perfectly fine parameterizations of the same curve, and they're very different, right? Okay, so they're different. And of course, there's nothing special about 2 here. I could have put cosine of 3t and sine of 3t, or cosine of 10t and sine of 10t. And in that case, I could have just modified this slightly, right? So in that case, if this were cosine of 10t, right, then my interval would be 0 to pi over 5, right? Would work. Okay, and then I would be going 10 times faster around the circle. Okay. So, one warning that this example should tell you is that there can be multiple parameterizations for a curve. I don't know why. It looks a little out of focus on my screen. Okay. Anyway, so there can be multiple parameterizations for a given curve. Now you might say, is there a best one? There is a best one for a number of reasons, but it's not as simple as that, and it's not a problem we'd have to worry about too much. I'll get into that a little bit later. But the point is that so long as you have a good enough parameterization, any of these computations that we are going to do work. So it doesn't matter that there's multiple parameterizations. If you have a parameterization in front of you that works, then that's good enough. Okay, and so you don't have to worry about that too much. And so what this means is that we tend to replace the curve C with its parameterization. So we tend to interchange the curve C with the parameterization R of t of C. And so in a lot of the language, that we use here, what we'll say, we mean the curve C, but we're going to say the parameterization. So we're going to treat this R of t as if it is the curve C, even though we know it's just one way of describing it, okay? So if there's ever any confusion about that, then you can let me know, but this is why I'm telling you this now. So a lot of times I'm going to say, consider the curve R of t is equal to blah, right? And what I mean by that is consider the curve with parameterization R of t, blah, blah, but I'm not always going to say that. Aaron asked, would the length of the curve be the same? Yes, Aaron. So the length of this curve is going to be exactly the same. That's right. Okay. And so here's the thing. There are some nasty curves, right, that you can think of. And here's a trick, not just for math. This is a trick for math, physics, computer science, chemistry, I guess, maybe. I don't know. This is a trick for not even just the sciences. This is a trick for critical thinking. Okay? So, the trick for critical thinking that I like to do is whenever you're given a definition of a thing, a very strict definition, right? So, for instance, a curve, right? So, you know what a curve is, or defined loosely. Your goal should be to think of the craziest possible thing that still satisfies that definition. Okay? So for instance, when someone asks you to draw a triangle, right? And they don't tell you anything else. They just say, draw a triangle. I want to know whether or not this property that I'm interested in is satisfied by any triangle. Right? So when someone asks you to draw a triangle because they want to test some general theory about the triangle, you do not draw this. Right? Don't draw that. That's too nice. Right? Of course, tons of stuff is going to be true for that triangle, assuming this is actually a triangle and is not butchered in this way. Right? So you shouldn't draw this. When someone asks you to draw a triangle, you should draw this. Right? That's what should run through your head. Okay. So whenever you're asked to draw some general thing, you should try intentionally to make it as bad as possible, as extreme as possible. Okay? Because if whatever general fact that you want to say is true for something like this, right? Well, then maybe you can say something, right? So you kind of want to intentionally make your examples as atypical as possible. So how does that apply to curves? So imagine I want to do some calculus on curves, right? So if I want to do some calculus on curves, and I say, draw me a curve that I'm going to do calculus on. Don't do this. Don't draw me this. Don't draw me this. Those are too nice, right? Don't even draw me this. Right? Draw me this. I didn't pick up the pencil there. Yeah, let's make it where did I start? Where's my starting point? Here? There. Okay, there's my curve. Okay, that's the curve you should think of in your head when I just say curve. Okay. So, of course, right? I can't do anything with this. This is terrible. Right? So I need to impose some conditions in order to be able to do calculus sensibly on this. Okay? And so what are those conditions going to be? Okay? Yes, I cut into the paper. See, look here. I went too hard. There it is on the next page. So, the point is we have to impose some conditions here. So when we talk about a curve, just saying curve, right, and a curve, just saying that it's okay if it's continuous, it's not good enough because that thing I drew, if I didn't rip through the paper, would have been a continuous curve. Okay, so that's not good enough. We need the curve to be smooth. Okay, so we need a notion of a smooth parameterization of a curve. Okay, and so there's two parts to this definition. So the definition is C is a smooth curve if it has a smooth parameterization. R of t, or t is in some set D. Okay. All right. But that doesn't help at all if I don't tell you what a smooth parameterization is. Okay. So R of t is a smooth parameterization if R prime, so if R of t is differentiable, that is as a that is as a vector valued function. So it has 3 component functions, and those are all differentiable. So if r of t is differentiable everywhere on D, and if r prime of t is not equal to the 0 vector for any t in the interior of D. Okay. The differentiable everywhere can be checked pretty easily. Okay. So the differentiable everywhere can be checked pretty easily by looking at the component functions and asking yourself, can I compute the derivative of each of those component functions, and is that derivative defined, right, and continuous for every point on D? So the question is, can I do that? Usually that's pretty easy to answer immediately. So then the thing to check is this condition. Now, this condition is going to cause you to be slightly confused at first, because you are bringing with you from Calc 1 some ideas of what r prime is, right? So we have a parameterization for a curve. It's a vector valued function r of t. We've talked about what the derivative of a vector valued function is algebraically, but we haven't talked about any kind of actual meaning behind it. And here I'm saying that a smooth parameterization, which is supposed to be a good thing, is one such that this parameterization doesn't, its derivative is not the 0 vector anywhere in the interior. Immediately, you're thinking, oh wait, like, the derivative of something being 0, that was a good thing. That was something I looked for in Calc 1. So what's going on here? This doesn't mean the same thing. Okay, so to show you that this doesn't mean the same thing, I'll do a single nice example. You might remember from Calc 2 that the ultimate strength of the parametric approach, right? If you weren't convinced by what I said before about this parametric approach, the point is that a parametric approach is more general than the actual approach, right? So let's say I have a function in the plane y is equal to f of t, and I wanted to graph this. Or actually here, whatever. I'm just going to use y and x here. So y is equal to f of x. So for example, let's start with everybody's favorite quadratic, y equals x squared. Okay, so you know how to do everything concerning this function, the analysis of this function. But you could actually write this function as a parametric curve. How? What's a parametric curve that parameterizes this function? Do you remember the trick? Right? So the way that you did this in Calc 1 was the following. You can use the parameter so x is just t here. So this would be ti plus, well, the parameter plugged into the function here, t squared j. Right? Where t is in all of R. So this parameterization, if you actually plot out what this is, well, it's exactly that parabola. All right? So this is a parameterization of this function. You can do this for any function, right? So it is nothing special about x squared here. You could do this for literally any function. Okay? So you can always parameterize a function. So actually a function is a special case of a parametric curve. Okay? And so all that stuff you did with functions you can now do in terms of parametric curves. So parametric curves are much better because they handle everything. They don't, you don't need to do anything else here. Okay. And so here's the thing, right? I know that if I take f prime of x and I want to know what is going on at f prime of 0. F prime of 0 is what? Well, we know that f prime of x is 2x. F prime of 0 then is 2 times 0, so it's just 0. So I know my derivative is 0 here, and I know that just from looking at it, right? This is exactly the canonical example of what it means when a derivative is equal to 0 for a curve, right? It has a horizontal, or it has a horizontal tangent line, right? Which means it turns like this, okay? It has a relative max or min, okay? So that's where the t squared j. Of course, if I didn't want to use t here, I could have written it as rx is xi plus x squared j. That works too, right? Where x is in r. So I didn't even have to call the parameter t. I could have just called the parameter x since I started with x up here. Okay, so, but here's the thing, right? Let's compute r prime. What's r prime of t? Well, it's the derivative of t, which is 1 I, plus 2t j. So what's r prime of 0? It's 1 I plus 2 times 0, so 0j, which is certainly not the 0 vector. Right? So we had a function here that we know the derivative of that function is 0 at this point, but when we view that function as a parametric curve, so if I have r here, r prime was not the 0 vector when the derivative of that function was 0. So in fact, it's never going to be the 0 vector, right? This is never equal to the 0 vector because the first component is always a 1, right? And so this is an example of a smooth parameterization for this curve C. Okay. So this is an example of where that condition that I had on the last page doesn't exactly mean what you think it might mean. Okay. So I'll do more examples of stuff like that. We'll talk about this next time. So next time we'll discuss how to find the length of curves and how to find tangent vectors and normal vectors to curves, which is the real stuff that we're interested in. All right. So that's that. So I will see you all on Friday, and hopefully I don't know how much I was slurring from my swollen face, but hopefully that will be less of an issue on Friday. So anyway, I will see you all then. I'll see you all on Friday. Remember, you have homework due tonight. You have discussion tomorrow. So remember that. In discussion, you'll be going over all this stuff that we've done in Chapter 12 so far. All right. Let me see some last questions here. What is an example where r prime of t is equal to 0? Brandon, I'll give an example like that next time. Aaron, so you're saying that for two equal parameterization, the derivatives can be different values? No. Oh, wait a minute. For two equal... It depends on what you mean by equal parameterizations. If you mean two parameterizations describing the same curve, then possibly. So, and I'll give examples of that too. So anyway, I'll see you all on Friday.